Welcome all. So, we are doing the multiple degrees of freedom system subjected to impact loading. In the last class, we looked into the orthogonality properties. We started with the proof of the orthogonality properties. So, today we will continue with the proof. So, now we are looking into the proof of the orthogonality. Okay. So, if we are dealing with phi r and phi s, basically phi r is nothing but the mode shape associated with rth mode and phi s is the mode shape associated with the sth mode. Okay. So, we have taken the modes corresponding to omega r and omega s. Okay. So, this mode shape is corresponding to the frequency omega r and this mode shape is corresponding to the frequency omega s, and this is the value of phi r and this is phi s. Okay. So, it must satisfy this particular equation. Okay. So, if it is doing that, okay, then we pre-multiply the equations with the corresponding mode shape. Okay. We pre-multiply with the mode shape. Okay. So, here in the first equation we are pre-multiplying by both sides by phi r. Okay. So, what we started is we started with the phi r and phi s term. Okay. So, here in phi s term we are multiplying it with the phi r term, pre-multiplying both the sides. So, it should remain same. Okay. After that we take the transpose of both sides of equation 18. Okay. We take the transpose in the equation 18. Okay. So, in the equation 18 we are taking the transpose. Okay. So, if we do that, it will result in this particular equation. Okay. And again we are pre-multiplying the latter by phi s. Okay. First we pre-multiplied by phi r, now we are pre-multiplying by phi s. Okay. So, this will yield this particular equations. Okay. So, if we subtract equation 21 from 20, okay, this minus this we are doing, okay, 21 minus 20 we are doing. So, we will obtain this particular equation. Okay. So, here, okay, the natural frequencies are distinct. Okay. Okay. So, if they are distinct, then this term must be 0. Okay. So, it establishes the orthogonality of the system. Okay. So, natural modes corresponding to the repeated natural frequencies are orthogonal to all other modes, but not necessarily orthogonal to each other. Okay. So, this way we have proved the orthogonality of the system, meaning if we multiply, okay, the mass matrix with the distinct mode shapes, okay, and the stiffness matrix with the distinct mode shapes, we are going to get 0. Okay. So, this is the first and the second orthogonality condition. Okay. And this is the proof of the system. Okay. Second property is that the modes are independent. Okay. The natural modes are linearly independent, meaning that one mode cannot be expressed as a linear combination of the other. Okay. So, expressed differently, the equation this one must be 0, because one mode cannot be expressed as a combination of the other. Okay. And this is only satisfied if and only if all the coefficients are 0. Okay. It means that if you look into simply, if this is the first mode, this is the second mode, this is the third mode. Okay. We cannot express the third mode as any combination of the other modes. Okay. So, the natural modes are linearly independent, meaning that one mode cannot be expressed as a linear combination of the other. We cannot express the third mode as a combination of 1 plus 2 or any other mode as combination of the other. Okay. So, this is what it is being represented out here. Okay. So, this is satisfied only if all the coefficients are 0. Okay. So, this is the proof of the independence of the modes. Okay. So, in order to prove this thing, we multiply the particular equation, okay, by mass times the mode shape. Okay. So, we multiply with the correspondingly mass times the mode shape. So, this is phi 1. So, transpose of this particular mode, phi 2, transpose of this particular mode, phi 3 and phi rth till phi nth. Okay. So, hence this term has to be, this becomes 0. Okay. Since M is a positive definite matrix, we have already established that M is positive definite matrix. Why? Because the, if you write it M in terms of the quadratic form, okay, then this is non-zero, okay, and we proved this by using the kinetic energy. So, kinetic energy is half mv square, okay. So, here kinetic energy and velocity cannot be 0, okay. So, then M also cannot be 0, okay. So, M is positive definite matrix, okay. So, the triple product cannot be 0, okay. Therefore, what remains is that CR must be 0, okay. So, using the same logic, all other coefficients must also be 0. It means that we cannot express the modes, okay, one mode as a linear combination of any other modes, okay. So, an important result of this independence is that any n dimensional vector, okay, any n dimensional vector can be expressed as a linear combination of the n characteristic vector, okay. So, this is an important corollary which can be derived from the independence of the modes, okay. All the modes are independent, okay. One mode cannot be written in terms of any algebraic sum of the other corresponding modes, okay. So, we proved the orthogonality, we proved the independence of the modes, okay. So, moving ahead, reality and positiveness of the natural frequency, okay. So, the natural frequencies are real and positive quantities, okay. So, the proof of reality. So, we start by assuming that the frequencies are not real, and we will show that this assumption leads to a contradiction, okay. So, what we do is that we start by expressing the frequencies as a real and a non-real part, okay. So, we are expressing this thing as a non-real number, okay. So, this is the expression for the frequencies, okay, in the non-real sense, okay. Since both k and m are real, it follows that the associated natural modes must also be complex, okay. So, then k and m are real. So, it means that the mode shape has to be complex, okay. So, we are expressing the mode shapes in terms of a complex formulation, similarly what we have done for the frequencies, okay. So, the complex conjugate of omega r and phi r must also represent a solution, okay. So, these are the complex conjugate, okay. So, this is the expression for the complex conjugate for the frequencies, okay, and this is the expression for the complex conjugate for the mode shapes, okay. So, using equation 22, okay, we use the equation 22 and substitute the above values, we will obtain this particular formulation, okay, meaning we are using the proof of the orthogonality. 22 was the proof of the orthogonality, okay. So, this was equation 22, okay, by which we proved the orthogonality, okay. So, we again take this equation out and we are substituting in the first case, okay. So, this is the same formulation of the equation, okay, and then we are writing down the expression for the frequencies, okay. So, this is how we write down the equation for the frequencies, okay. So, the triple product of the matrices in this equation is a real quantity, okay. Since the matrix M is positive definite, okay, we know that this mass M, this is positive definite, it means that the value, if we express it in the algebraic sum, the algebraic quantity is greater than 0, okay. This product is a non-zero positive number, okay. So, the triple product has to be is a non-zero positive number. What it means that beta must be 0 in order to satisfy this term, the expression for the term beta, okay, this has to be equal to 0, okay. So, omega r, the frequency cannot be complex as assumed in equation 25, okay. So, if beta equals to 0, then omega s and omega r are non-complex numbers, okay, they are real number, okay. So, it must be real. So, this is how we prove that the frequencies and mode shapes are real number, okay, they are not complex number, okay. So, we started with the orthogonality, okay. Then we proved the independence of the modes, and then we proved that the frequencies and mode shapes are real numbers. Okay. So, we have proved the orthogonality, independence and the realness of the frequencies and the modes. Okay. Moving ahead. So, proof of positiveness. Okay. So, pre-multiplying the expression for relating stiffness and mass by phi term, we obtain this term. Okay. Therefore, omega r is either 0 or positive. Okay. However, if a system cannot undergo rigid body motion, okay, the left handed member of such equation is non-zero and positive. Okay. This one is non-zero and positive, hence omega r is non-zero and positive is used in this type of cases. Okay. So, in order to summarize this thing, if the system is stable and cannot perform rigid body motion, okay, then the non-natural frequency will be non-zero positive values. Okay. There will be a non-zero real frequency. Okay. In case of a rigid body motion, okay, the frequencies can be 0, okay, but in the case of a flexible system, the frequency will be a non-zero real number. Okay. So, moving ahead, we define a term called the modal participation factor, okay, for that particular mode. Okay. So, this is the expression used to write the modal participation factor. Phi r is nothing but the mode shape corresponding to the mode r or corresponding to the frequency. Omega r, m is the mass matrix of the system, and 1 is the influence vector representing unit displacement in the direction of the excitation. Okay. So, if the system, if you are looking into the system and if you are looking into the rth mode, then 1 is the influence vector representing the unit displacement in that direction of particular excitation. Okay. The participation factor basically means that it measures the extent to which each mode contributes to the overall dynamic response. Okay. Remember, we earlier said that the total value, okay, of the displacement or the chosen degree of freedom, okay, is a combination of all the modes. Okay. So, for each degree of freedom, all the modes are going to contribute. Okay. The first mode may contribute 90%, the second mode might contribute 6% and so on and so forth, but the total y, okay, or the total value of the displacement, okay, or the total value of the chosen degree of freedom will be a combination or will be made up of contribution from all the modes. Okay. So, this tau r or the modes participation factor is a measure of this contribution, okay, how much one mode is contributing to the overall response of the system. Okay. So, the participation factor measures the extent to which each mode contributes to the overall dynamic response in the given direction. Okay. The square of this factor is related to the effective modal mass, showing how much the mass participation factor is in that mode. Okay. How much is the mass, what influence of that particular mass in that particular mode. Okay. So, each mode, how much each mode is contributing to the displacement in that particular direction. Okay. So, this is the modal participation factor. Okay. Okay. So, let us take a dynamic system. Okay. So, we have taken a system in which we have 3 degrees of freedom. Okay. The mass is concentrated at the various floors. Okay. So, this part we can assume it to be rigid and the flexibility is being provided by the column only. Okay. And the stiffness, okay, is represented by K1, K2 and K3. Okay. X1, X2 and X3 are the chosen degrees of freedom out here, and we have excitation applied at each degree of freedom. Okay. So, if we try to draw the free body diagram of the system, okay, so P3 is acting on the mass M3 using the D'Alembert principle. The pseudo acceleration is given by M3 X3 double dot. Okay. This is the inertia term, okay, and this is the contribution of the stiffness of the particular term. Okay. the system is moving in x3 direction and x2 direction. Okay. So, the net engaged displacement is x3 minus x2. Okay. So, that term will come as the stiffness, okay, the contribution from the stiffness term. Okay. And similarly, we do for the other degrees of freedom. Okay. So, equations of motions are obtained by application of the procedure described earlier, okay, which is given out here. Okay. So, we consider the system in a deflected configuration and identify all the forces acting on it, okay, including the D'Alembert's inertial forces. Okay. So, this is the inertial forces given by the D'Alembert's principle. This is the effect of the externally applied loading, and this is the effect of the stiffness in the system. Okay. So, if you write them down, here we are getting the free body diagram, and from the free body diagram we can write down the equation of the motion. Okay. So, same thing we repeat for the other 2 degrees of freedom. We write down the inertial forces by the D'Alembert's principle, that the pseudo force, external force acting on this particular system, and the value of the stiffness. Okay. So, in this way we write down the equation of motion for the entire system. Okay. So, draw a free body diagram which is given out here for the individual masses and write down the equations expressing in the equilibrium of the forces. Okay. So, from here to here we drew the free body diagram. In the free body diagram we labeled all the forces, and from the forces we can write down the equation of motion of the particular system. Okay. Okay. So, here we are representing the equation of motion. Okay. So, let us do one at a time. Okay. So, we have taken the first one. Okay. So, first one, the inertial forces represented by the D'Alembert's principle, m1 x1 dot, m1 x1 dot. Okay. The external force applied P1, the external force applied P1. Okay. The relative stiffness in the system. So, this way it is going to move x1. So, stiffness is K1 x1, K1 x1. Okay. From the top part, okay, this stiffness will be also acting in the system. So, this will be in the other direction, K2 x2 minus x1. So, K2 will move x2 minus x1. Okay. So, K2 x2 minus x1. Okay. So, similarly mass m2, the inertial term, okay, the external force is P2, and then K2 is acting this way. For this particular one, K2 is acting this way and K3 is acting in the opposite direction. So, here the direction of the K2 will change and K3 will be the contribution from the top spring. Okay. So, inertial forces, external forces, and the contribution from the spring. Okay. Similarly, for the 3rd degrees of freedom, so this is the contribution of the inertial forces, the contribution from the external applied, and the contribution from the stiffness. Okay. So, inertial, stiffness, and the external applied load. So, external, inertial, and the stiffness factor. Okay. Then we arrange them neatly into a matrix formulation. Okay. So, here we can see, since we have used the lumped mass approach, my mass matrix is diagonal. Okay. The non-diagonal terms are 0. Okay. So, this is the mass matrix M, and this is the acceleration component. Okay. Then we have the stiffness matrix, okay, given by K, and the displacement vector x, and the externally applied forces given by P. Okay. So, this is the diagonal terms, okay, and if you look into the non-diagonal terms, we see that the matrix is symmetric. Okay. So, this establishes whatever we have learned earlier. Okay. Mass matrix is diagonal, off diagonal terms are 0, stiffness matrix is symmetric. Okay. So, this is the representation, the matrix representation of the degree of the particular system. Okay. So, we take a simple case in which we are taking the value of all k's as equal, okay, and all m as equal. Okay. So, m1 m2 equals to m and m3 equals to half of m, okay, and the forces are 0. Okay. So, basically if the external forces are 0, okay, then this system is going to go into a free vibration undamped system. Okay. The damping is 0, C equal to 0 in this particular system, and the externally applied load is 0. So, this will be in the free vibration case. Okay. So, we formulate the eigenvalue problem, okay, and here we are solving the eigenvalue problem. Okay. So, this is our formulation of the eigenvalue problem. Okay. So, first what we are trying to do is that we are trying to evaluate the frequency of the system and the corresponding mode shape of the system. Okay. So, these things we are first trying to evaluate. Okay. And we have, since we have assumed the externally applied loads to be 0, so this directly becomes the free vibration problem. Okay. So, for a non-trivial solution, the determinant of this particular matrix. So, for the non-trivial solution, the determinant of this particular matrix should be equals to 0. Okay. Det of this guy has to be 0. Okay. So, we evaluate the determinant of the system. Okay. So, we get a cubic equation, okay, and we solve the roots of the equation. Okay. And from the roots of the equation, we get the value of the frequency of the system. Okay. So, this frequency will be, okay, so the frequency will be root over this term. Okay. So, this is the first frequency, okay, second and the third. We are arranging in the increasing order. Okay. So, this one, the lowest one is also called the natural frequency of the system. Okay. So, after that we will put back the value of omega in the particular equation, and we will try to calculate the value of the corresponding mode shape of the particular system. Okay. So, substituting the value of each lambda or the value of the corresponding omega, we solve for the different. So, one by one we are putting the values of lambda. Basically what we are doing is that we are putting back the values of the different frequencies, and for the different frequencies what we are trying to do is that we are trying to calculate the particular mode shape corresponding to the first frequency, corresponding to the second frequency, and corresponding to the third frequencies. Okay. Okay. So, taking phi equals to 1 and solving equation 3.9, we get the value of the mode shape. This is the mode shape corresponding to first frequency, okay, and then we repeat the same thing. Here we have put the value of lambda, that is corresponding to the first frequency omega 1, then we will put lambda 2, the value of lambda 2, and calculate back all the phis. We will get the phi 2, and then we will put the value of lambda 3, and then we will get the value of phi 3. Okay. So, this is the value of the first mode, second mode, and the third mode. Okay. So, first mode intuitively we know that this is being represented by a cantilever, okay, and in a cantilever we know that this is how the mode shape is going to look like. Okay. So, we have chosen our degrees of freedom at these 3 locations. So, the first location the value is unit, second location 1.732, and third location is 2. Okay. So, this one agrees with our earlier notion of the mode shape. Okay. So, intuitively we know that this will be correct. Okay. So, for the second mode, okay, we know that second mode is going to look something like this. Okay. So, now if we will look into the value. So, the first value 1 unit this way, 0, and 1 unit this way. Okay. So, this intuitively agrees with the this particular shape. Okay. And the third mode looks something like this. Okay. So, this is the first cantilever mode, second cantilever, and this is the third cantilever mode shape. Okay. So, here if you write down the value 1 minus this way and then positive this way. Okay. So, this again agrees with what is the intuitive value we know for a particular cantilever. Okay. So, this way we can say that the evaluated values are correct and they agree with our notion of the mode shape that we have already established. Okay. So, moving ahead, till now what we have done is that we have evaluated a system, okay, in which we assumed that the forcing function is 0 and the damping was also 0. So, we evaluated the frequency of the system, we evaluated the corresponding mode shapes of the system. Okay. So, now what we are going to do is that we are going to add one complexity to the system. We are going to add the damping in the system. Okay. And damping will be represented by the viscous damping. Okay. So, analysis of multiple degrees of freedom system of a damped system. Okay. Now, the damping is also present in our system. Okay. So, in the analysis of a damped system responses, viscous damping will be assumed. It means that the damping will be assumed to be proportional with the relative velocity, okay, and multiplied by a damping coefficient. So, this term represents the viscous damping coefficient. Okay. So, the damping forces, it might be caused due to any type of phenomena, but we are representing it using a viscous damping part. So, the damping forces Fd is expressed as a linear function of the velocities of the coordinates. Okay. So, this is a viscous damping, this is a representation of the viscous damping. Okay. So, normally we use viscous damping formulation in our multiple degrees of freedom system analysis. Okay. So, in this equation, the matrix C represents the damping matrix of the system. The element Cij, which corresponds to the ith row and jth column, indicates the force at node I induced by a unit velocity of mode j. Okay. So, earlier in the case of mass matrix and stiffness matrix, we were expressing this thing as the force induced due to the unit acceleration in case of mass matrix and unit displacement in case of the stiffness matrix. Okay. So, now we are expressing the same terms in terms of the unit velocity. Okay. Why? Because the damping is represented as a linear function of the velocity. So, if we introduce damping into our system, okay, so we earlier had the inertial term, okay, we had the stiffness term, we had the external forcing term. Now, we are introducing the damping term. Okay. So, this part is represented by the damping. Okay. So, similarly, in terms of the flexibility of the matrix represented as D, it can be expressed as this formulation. Okay. So, here what we have done is that we have pre-multiplied by the flexibility matrix, okay, and since K and D are inverse of one another, so this becomes a unit matrix. Okay. So, this is the formulation, okay, or this is the most commonly used formulation in terms of the stiffness formulation, and this is the formulation in terms of the flexibility matrix. Okay. The structure of the matrix C, the damping matrix, clearly depends upon how the damping resistance is distributed throughout the system. Okay. So, right now what we have seen is that we can directly calculate the mass matrix, we can directly calculate the stiffness or the flexibility matrix. Okay. But unlike the element of mass, stiffness and flexibility matrix, okay, which can be determined from the basic properties of the structural element. Okay. So, remember, in order to calculate the mass, stiffness and flexibility, we use the distributed mass, we use the area, we use the second moment of area, we use the modulus of elasticity, nu and other basic properties. Okay. But in case of damping matrix, it becomes tricky, because C we are the damping coefficient C, it is a representation of the damping. Okay. It is not the actual damping in the system, we are representing it by a viscous damping coefficient. Okay. So, the direct calculation becomes cumbersome, tiresome, and this is not the proper justification. Okay. Because this is just what we are doing is that we are representing the effect only. Okay. Cause might be due to some other mechanism, but we are representing just the effect by a viscous damper. Okay. So, this is in contrast to the mass and stiffness matrices, which are direct properties and can be directly calculated, but this damping property is not a direct property. Okay. So, we are using just a representation. Okay. So, C cannot be so evaluated as the relative magnitude and the distributions of the various factors which contribute to the damping of the structure are generally not known. Okay. So, damping itself is a very complex phenomena. So, what we do is that we just looked into the effect, okay, what damping is doing to the system, and we take down this effect and we represent it using a viscous damping. Okay. So, that is why we cannot directly calculate C. Okay. So, the factors that contribute to the overall damping of the system include the resistance posed by the fluid, okay, such as the air or water surrounding the structure. Okay. So, if there is a pocket of any type of fluid, air, water or anything or any other viscous material, so that will affect the damping in the system. The energy dissipation resulting from the deformation of the structural elements. Okay. So, the energy dissipated, okay, which results from the deformation of the structure. Okay. So, one energy will be stored, other types of energy will be dissipated. Okay. So, the effect of the damping will come into this part, the energy dissipation. Okay. Then there will be the losses occurring at the contact surface of the cracked section. Okay. So, if the section cracks, okay, let us say in case of RCC beams and columns, okay, there will be a cracking in the system. Okay. So, there will be some losses occurring there. Okay. So, this will contribute to the damping of the system. Friction and joints at the supports. Okay. So, if there are friction at joints and supports, so this will contribute to the overall damping in the system. Any other energy absorption, okay, that might be attached to the main structure. Okay. So, all the energy absorbing mechanisms, okay, they will show up as damping in the system. Okay. And that damping we are representing as a viscous damping. Okay. So, that is why the analysis of this all this phenomena, their understanding is still lagging. Okay. So, what we do is that we take the overall effect, okay, overall how much is the damping in the system, and we represent it using the viscous damper. Okay. See x dot. Okay. So, this damping is the representation of the total effect. Okay. Whereas, the mass and stiffness, they are the properties which can be calculated from the basic values. Okay. So, I will stop here. We have discussed about the damping today, and we will continue the next lecture. Thank you.